All right, class. So this is just a review as to our overall process of data analysis. So we have a group that we're interested in, which we call a population. There's usually too large to do any analysis on, so we take a piece of that group called a sample. Okay? From that sample, we calculate statistics, specifically the sample mean and the sample proportion. Okay? These are used to estimate the population mean and the population proportion. Like I said, sometimes your book uses pi as opposed to p, especially when you use p as the sample proportion. So I'm going to assume that you find a book that uses pi as a proportion. Okay? So far we've done a lot of analysis on what about the mean this, the mean that. But there are ways that you can look at an interpretation of the proportion. So here's what I mean. Let's say I have a data set and I have the numbers 4, 2, 7, 3, 8, 9, 12, 0. I'll do a couple of more. 15, 7, 3, 6. Okay, so I have a sample of size 12. Okay, and the question could be, what proportion of the values are less than 6? Okay, so clearly you can see from a proportional standpoint, P is equal to 1, 2, 3, 4, 5. Okay? 5 out of 12 would be the number of successes. Okay? And so this could be used to estimate the number of the percent of values that are less than 6 in this proportion, in this population. So again, we calculate our sample to say something about our population parameter. So keep that in mind because your textbook does not really give you examples of proportions, but when you look at the literature, you will see a lot of proportions used. So we're going to keep that in mind. But for now, let's stay with this whole idea about the sample mean predicting the population mean. Okay, so I have my data set. Okay, I have some data, and I collected a sample mean on it. Now, what do we remember about the distribution of the sample mean? Number one, we know it's centered at mu. Okay, so the center of it is the population mean, and we know that its standard deviation, of the sample means, is called the standard error, and it has a size of sigma over root n. Okay, so on each side of this you have sigma over root n. And so if you're looking to find out, what it's the likelihood that a value is less than 2 or less than 3 or whatever, you can find that value on your chart, find out that shaded area, and you can do the proportion, the probability of observing that. So what we're actually end up getting into is this idea of a hypothesis test. Okay, so this is the first section in inference. And here's the basic idea. Okay, number one, you have some assumption or a belief. Okay, and so in this case, let's assume that I believe that the population mean is 30 or 3 or whatever. I guess my pen just wrote a 3. I don't like 3. Let's say I believe that my population mean is 5. Okay, that's what I believe about the population, but I don't have enough pieces of information. I don't have the ability to check the entire population. So I take a sample and calculate the actual sample mean. Okay, and the sample mean turns out to be 4.6. And it's based on a sample of size n. So the ultimate question is 4.6 far enough away from 5 to suggest that this in fact is not true? Okay, so here's the idea. Okay, so first I have an assumption. Second, I have to find my sample statistic. And then third, I actually test the sample statistic. So here's the idea about the test, okay? So test statistic. So keep in mind, I want to see if the null, if the sample mean is 5. Okay? So let's make another page. If in fact the population mean is 5, that means that it is centered at 5. Okay? So we're going to assume that it is 5. Right? And then you have the value of 4.6, which is what I'm interested in. So the question is my mean 5? And then if it's not 5, how far away from 5 is acceptable to say, you know what, that's close enough? Is that number 4.92? Is it 5.10? Is it 4.99997? So the closeness of the value really determines whether or not you can say that the mean really is 5. So what you want to do is find the probability of observing something of what you observed, your sample mean, or further out. Okay? So in other words, if the true mean is 5, what's the likelihood that I would get a number of 4.6 or lower? Okay? This information gets to an idea called the p-value. So the p-value tells you the probability of observing your test statistic assuming your first assumption is correct. Then that first assumption, mu equals 5, that is called your null hypothesis. Okay? It does not say that the mean is in fact 5. It says that you believe it's 5. And so you want to collect data to see if in fact it's likely that it is in fact 5. Now the truth is, it could either be 5 or not 5. And if it's not 5, it could either be less than 5 or greater than 5, or you may not consider and just say does not equal 5. Okay? And if you just don't care about whether or not it's less than or greater than, that's called a two-sided test. Okay? But if you want to test whether or not it's either 5 or less than 5, that's called a one-sided test. But for argument's sake here, we're going to look at a two-sided test. So if it is not 5, your alternate hypothesis is that it's not 5. So we're going to give it the benefit of the doubt and say, okay, we're going to think it's 5. If it is in fact 5, that means that the center has to be at 5. Now that I observe my data, I got a sample mean of 4.6. I want to know how far away it is from the mean to see what's the likelihood of observing something like that. Now we remember from earlier that the sample distribution, the distribution of the sample means is in fact standard normal with mean mu and standard deviation of sigma over root n. Okay? So if we know sigma, we can plug that in. And in this case, let's assume that we know sigma. And let's say we think that sigma is 2. Let's assume we know that. Okay? Then the other thing we need to know is how many samples did I take to create my sample mean. In this case, we assume we took 20 samples. Okay? So that means that in my example, the distribution of the sample means would be normal, 5, which is the middle, 2 over square root of 20. Okay? So that could simplify, you could pull out a 2 and say it's 1 over square root of 5 if you wanted to. But this is, in fact, the distribution. So now, with that distribution, you just plug in and try to standardize your value under those situations. So my value is, of course, 4.6. Okay. So 4.6. That's my value. And I'm going to subtract off the mean, which is 5. So 4.6 minus 5 over, and this is 1 over the square root of 5. So I really have negative 0.4 over, nope, negative 0.4 times root 5. Okay? And, you know, you can pull a calculator out here, and you would get negative 0.4 times square root of 5, negative 0.894. Okay? So you have negative 0.894 as your z statistic. And from here, it's exactly what we did before. We just find out the area that's less than a negative 0.89. Okay? And so once you find that area out, what you're getting is this area here, which is called your p-value. Okay? So if that area is small, and actually I can tell you what that number is. So if you give me a second, what we're looking at is the area less than negative 0.89. So stat 2 bar negative 0.89. That's 0 and 1. Comma 0, comma 1. And we're looking at about 0.123. So about 0.13. Okay? So this is equal to, so the probability that z is less than negative 0.89 is about equal to 0.13. So what that's telling us is that there's a 13% chance that you would observe a 4.6, assuming that the true middle was 5. So then the question still remains at this point, is that far enough? And in order to answer whether or not that's far enough, we have to first consider how confident we want to be in our finding. Okay? So this is all fine and dandy, but now since we have a number, we actually kind of did it in the wrong order, but now since we have a number, we need something to compare that to. Okay? If we want to be 95% confident, and let's assume that we do, okay, so we have a p-value of 0.3. We have a p-value of 0.3. We'll keep that at 0.13. We'll keep that up there. But if we want to be 95% confident, then we're going to need to compare it to the z value or the significance level at 95. So a 95% confident means that I have 0.025 out here and 0.025 out here. And you would see that z equals 1.96, both positive and negative, cuts off the middle 95%. So if that's the case, my alpha level is 0.05. It's the area that's outside of my middle part. Okay? So a significance level of 0.05 is equivalent to the 95% confidence level. So here's the key. If your p-value is greater than alpha, you do not reject H naught. Okay? So that means that you're willing to accept being wrong 5% of the time, or said another way, you know, if you saw something that happened less than 5% of the time, you'd be okay with it, or more than 5% of the time, you'd be okay with it. This actually can happen 13% of the time, so it's more common than you are willing to accept. So you say, okay, well, maybe in fact it is 13, or whatever the middle was. The middle was 5. So I don't have enough evidence to suggest it's not 5, because that area that I calculated was bigger than what I was willing to give it anyway. So if that's the case, you do not reject H naught. You can come up to that same conclusion by saying that the z value that you create is greater than is less than 1.96. Okay? These are synonymous. So when you plot your z value and compare it to the z that you calculated, you'll see that 1.96 would be further out than whatever your z value was. Okay? On the other hand, if your p-value is less than alpha, okay? So if p is less than alpha, we reject H naught in favor of the alternate hypothesis. So what we're basically saying is, we assumed that the mean was 0.5. We did a calculation, came up with 4.6, and the p-value of this was 0.03. That's saying that 3% of the time, I should be able to observe a value as far away from this 5 as what I calculate. So 3% of the time, I should see a 4.6 or worse, or less in this case. Well, I'm willing to accept it 5% of the time, but not 3% of the time, so it's unlikely that the true center of this is 5. So if it's unlikely that the true center of this is 5, that means that the mean of the population is not 5, which was our original assertion, so our original assertion has to be incorrect. Okay? So we would reject the null hypothesis. This is similar by saying that z, your calculated z, is greater than 1.96. Again, it's going to cut off a smaller area than the 0.05 that you're interested in. And so you decide that, no, I'm convinced that the null hypothesis is not true. Now, having said this, there's a whole other conversation about a type 1 and a type 2 error. It's important to realize that we're not saying, let's say that we did not reject the null hypothesis. We're not saying that the null hypothesis is right. What we are saying is we don't have enough evidence to suggest that it's wrong. It's very similar to whether or not you can convict somebody of a crime. Even if that person is not innocent, if you don't collect enough information, you cannot convict them. So you'll let that person off. They're not innocent, but you can't convict them, so they're not guilty. That's kind of like what happens with what's called a type 1 error. Okay? That's actually a type 2 error. The type 1 error would be if I, in fact, convicted an innocent person. In some cases, that's a worse crime than letting somebody off who, in fact, did the crime. So when we talk on Monday, we'll talk about the differences between the type 1 and the type 2 errors and how that affects your findings. But this is a general conversation about a null hypothesis testing. So to summarize, okay, here's the gist of it. I believe that the mean is some value. Okay? So I would state mu equals A. Okay? I have to also state my alternate hypothesis. In this case, mu does not equal A. Now I calculate my statistic. So I calculate my sample mean, okay, equals some value. Okay? And then I calculate my z statistic based on this, because once I have x bar and I have sigma over root n, I can calculate a z statistic by doing my mean minus the expected mean, which is the population mean, over sigma over root n. Okay? This is my statistic that I'm looking at, my test statistic. So if this number is greater than 1.96 at the 95% level, or 2.575 at the 99% level, or 1.645 at the 90% level, then I would reject H naught. Otherwise, I would fail to reject H naught. Not saying I accept it, I'm just saying I don't have enough information to reject it. Okay? So this is step 1. This is the first of my videos. The difference between this video and the next video is that here we're assuming the standard deviation is known. But if you think about it, this term here is a function of the sample mean, of the population mean, which we normally don't know anyway. So I have to estimate sigma as well with S, which is the sample standard deviation. And since I have to use an estimate of my population standard deviation, I have a sample standard deviation I have to plug it instead. This no longer becomes a Z statistic, it becomes a T statistic. And the critical value I'm comparing it to will be found on the T table as opposed to the Z table. And it's not as simple as saying, 19625751645 if I have the S in there. What I have to consider at that point is how large of a sample I have, which determines my degrees of freedom, and how confident I want to be. So I'll have a different value for each combination of confidence level and degrees of freedom. Final point before I let you go. When we're talking about calculating a T statistic for the correlation, it was n minus 2 degrees of freedom, which means if I had 20 pairs, I would have degrees of freedom of 18. But we're talking about sample means. If I had 20 values and I calculated a sample mean of 20 values, it's no longer n minus 2 degrees of freedom, it's n minus 1 degree of freedom. So I would look at the 19 line in the T statistic. So that's it for now. I will talk to you guys in a bit. Take care. See ya. Okay. One sample hypothesis test. Let's see.